Every modern language model, from chatbots to coding assistants, is built on one idea that sounded almost too simple in 2017. Attention is all you need. The original transformer paper made a bold move. It removed recurrence and convolutions from sequence modeling and used attention as the core computation. Before transformers, many sequence models processed text step by step that made long-range dependencies harder and training less parallel. The transformer is an encoder-decoder model. The encoder reads the input sentence. The decoder generates the output sentence one token at a time. First, words are split into tokens. Each token becomes a vector, so the model can do geometry instead of manipulating raw text. But attention alone does not know order. The model sees a set of vectors, so we must inject position information into each token. The original paper used sinusoidal positional encodings. Different frequencies mark different positions, giving the model a sense of word order. Self-attention lets every token look at every other token. The word, it can focus on the animal, the action, or the object, depending on context. Attention starts by projecting each token into three vectors: query, key, and value. Query asks a question. Key says what a token contains. Value carries the information. The scale dot product attention formula is softmax of qk transpose divided by square root dk multiplied by v. This is the heart of the transformer. Q times k transpose creates a score matrix. Each row tells one token how much it should attend to all other tokens. Softmax turns raw scores into probabilities. Strong connections become large weights. Weak connections become small weights. Then the model takes a weighted sum of values. The new token representation becomes a context-aware mixture of relevant information. One attention pattern is not enough. Multi-head attention runs several attention heads in parallel, so different heads can learn different relationships. An encoder layer has multi-head self-attention, then a feed-forward network. Residual connections and layer normalization keep training stable. The feed-forward network is applied to each token separately. Attention mixes information across positions, while the feed-forward part transforms each position. The paper stacks this block multiple times. Each layer refines the representations, from local word patterns to more abstract sentence meaning. The decoder is special because it must not cheat during generation. Masked self-attention blocks every token from seeing future tokens. After masked self-attention, the decoder uses encoder-decoder attention. This lets each output token look back at the input sentence. At the end, a linear layer and softmax produce probabilities over the next token. The decoder repeats this until the sentence is complete. Training is simple in principle. Given the correct previous tokens, predict the next token, and minimize the negative log likelihood. The key advantage is parallelism. During training, all input positions can be processed together, unlike recurrent models that move step by step. But full self-attention has a cost. The attention matrix grows with sequence length squared, which is why very long context is expensive. Modern language models usually use the decoder side of this idea at massive scale. The details changed, but the core attention block stayed recognizable. The transformer is powerful because it turns sequence modeling into parallel attention, position signals, feed-forward transformations, and next token prediction.